I'm very happy to be here, so I'd like to thank the organizers for giving me the chance to give a talk in such a nice conference. Indeed, so this talk is a kind of continuation of my last year's talk here. So, and the former half, I'll talk just a review of the last year's talk. And the latter half, I would like to talk some progress on this project. So partially, so this work is joint with Masaki Kashiwara. Okay.
So it's a few university in Tokyo, yeah?
Yeah, that's right. Yes.
Interesting name, yeah. It's not
so okay. So right, I'll explain you. Okay, so this is the basic references, and then the last two is the basic reference in my talk. But the last one is still in preparation. Okay. And then this is a picture, so just related to my talk. So this line is already established. So quiver Hecke algebra R, and R gmod is the category of. Okay, so R gmod is the category of finite-dimensional graded modules. So category 5, this one is just the quantum coordinate ring. And also this has a crystal structure, so this crystal base is isomorphic to B of lambda. This is the crystal base of UQ minus. Okay, so today I will talk on this line. Okay, so tilde means that just the localizations. Okay, so we consider the localization of some monoidal categories. And then so we can consider the categorizations, and then we have some localized quantum coordinate ring. And also this has a crystal, so-called cellular crystals. Okay. So there are some basic notations. So first we set G is a simple Lie algebras, but later it will be Kac-Moody Lie algebras. Okay, so simple roots, simple co-roots, and root lattice, and then weight lattice, and Weyl group, UQG, and the subalgebras. Okay. And the quantum coordinate ring is just defined as a restricted dual of UQ plus. Its definition is like this. Okay. And indeed, as algebras, so UQ minus and AQN are isomorphic each other. Okay. But this product is usually obtained by so-called quantum shuffle algebras, quantum shuffle product. So this algebra is embedded in so-called quantum shuffle algebras. Okay. Okay. So let's see crystal base. So this is the basic definition. So, but it's very long, so I want to omit some parts. Anyway, so A is a subring of Q of Q, regular at Q equals 0. So then we can consider everything just goes to 0. Okay. Here, a pair L and B is a crystal base of modules M or UQ minus if it satisfies the following conditions. First, L is a free A submodule of M. And then, so we just extend the coefficient Q of Q, then so we recover M again. And the L has also the weight decomposition. And the B is a basis of Q vector space L over QL. So this means so B is a basis at Q equals 0. And it has also it is also a weight basis. Okay. And then so we have some so-called Kashiwara operator, EI tilde and FA tilde. It acts on L naturally. But important points of crystal base is number 4 and number 5. Number 4 says EI tilde still act on this basis. Okay, so it means so basis is just a set. No linear structures, no algebra structures, just a set. But still, EI tilde if EI tilde acts on B. It means EI tilde if EI tilde just moves basis element to go other basis element or 0. Okay. or 0. Then so, and also number 5 means so EI tilde, FI tilde almost inverse each other. If it goes to 0, it cannot go back. But if it goes to other bases, it can go back EI tilde, FI tilde. They are almost inverse. Okay. And then so Kashiwara shown that there exists a crystal base L of lambda and B of lambda, or L of infinity, B of infinity. They are the crystal base of B of lambda. B of lambda is irreducible highest weight modules with highest weight lambda, or UQ minus. Okay, so this is the definitions. And then so as I said, B has such good properties. Then so B has a natural graph structure called crystal graph. This graph is each vertices are from B, and each arrows is defined like this. The action by phi tilde gives the arrow I. So B has natural graph structures. It's called crystal graph. Okay. And one of the most important property of crystal base is tensor product structures. Okay. So if we have a LB BJ, LJ BJ, it's a crystal base of MJ, J equal 1, 2. Then so we consider the tensor product. So naturally it becomes the tensor product, crystal base of tensor product M1 tensor M2. And also the Kashiwara operator's action is described very simply. So indeed on tensor product, if I tilde, E tilde act on left or right. This case is controlled by the following function phi I and epsilon i's. Here phi I is so look this string here basis B, basis U here, and then so phi I means how many times we can go forward from U by Fi, and epsilon I means just how many times we can go back from U by EI tildes. Okay, so this value just control the action of Kashiwara operators on tensor product. Okay. Then so crystals. Crystals is just a combinatorial object, abstract object. It's just coming from the property of crystal bases. Okay, so 6 tuple B weight epsilon phi EI tilde Fi tilde is a crystal if B is a set. And also there exists some special element 0, it's just outside B, and maps here. And they satisfy the following conditions. But the important is number 4. This condition is coming from this number 4, this one. Okay, crystal base, definition of crystal bases. Okay, let's see the example. So of course, crystal bases, B of lambda and B of infinity is just a crystal. They are already crystal. This one or this one. But basically, crystal is just, as I said, it's just combinatorial object, so it has no representation theoretical background. But some of them it has, but some of them do not have. Okay. Then see the examples. So take index I, and Bi is a crystal. Each element is parameterized by an integer n. Okay, so as I said, so Bi is the same as just the integer set of integers. Okay, and then its crystal structure is given by these formulas. Especially important is this one, this red part. EI tilde action by EI tilde and Fi tilde is just like this, n to n plus 1 and n to n minus 1. Then the crystal graph structure is like this. 0 goes to minus 1, minus 2. This is an infinitely long crystal graph. And there is no other arrow, just only I, arrow I. And other arrow not appear. Okay. And then, so as I said, so crystal has a tensor product structures. Then, so we can consider that their tensor product, BI1 and so on, tensor BIM. Here we denote the element in this tensor product is like this, x1 and so on, xm. It's these are just integer, okay. And then, so it's really complicated, but anyway, so important is this function. It's defined on this set. And sigma k is from here 1 to m. This function just dominates the structure of these crystals. It's really complicated, so I don't say anything here. So, but anyway, it's completely determined by this function. Okay. And then we call this crystal, if I1 and so on, IM is a reduced word of Weyl group. We call this such crystal is a cellular crystals because this crystal is obtained by some tropicalizations of positive geometric crystal on the Lagrange dual of Schubert's cell. Schubert's cell has a geometric crystal structures, okay? And then we can consider the tropicalizations and we have such crystals. So then we call this one cellular crystal. And then so I and my student Kanakubo showed that so this crystal is connected in the sense of crystal graph. So it means so each element just connected by arrows, okay? So right there it's important. Okay, so let's see the more structure of BI. BI is a cellular crystal. So we take I is the longest reduced word. N is the length of the longest element, capital N. Here, function beta k is defined the subtraction of this one, so sigma k plus minus sigma k. Here, k plus is defined like this. It's just the index nearest k, and they have same index, ik and ik plus is same, but k plus is bigger than k. But sometimes it doesn't exist. In that case, we set it's n plus 1. Okay. Then, so consider the hi is a solution space of these inequalities. Okay, beta k x equals 0 inside here. So here I don't say I should say yeah. So here. So BI is sometimes identified with Zn, okay? Okay, so this space has a good property because it has an integer basis, h1 to hn, okay? h1 and so hn is defined by this formula, okay? So this has a free Z lattice with basis h1 to bold h1 to bold hn. Okay, so right there it has some meaning in categorizations. Okay. Okay, so let's see how to show the connectedness of BI. B of infinity, as I said, this is a crystal of UQ minus. So please note that B of infinity is realized in this crystal by considering, for example, a polyhedral realizations. Indeed, type A case, G equal A2, this is SL3. B of infinity is parameterized by three integers x1, x, y, z. And they satisfy these inequalities like this. So this is a subset of Z3, and this is same as B1 to 1. 1 to 1 is the longest element of A2, Weyl group of A2. Okay. So it means so we want we should to obtain B of infinity, we just abandon some part of BI. So outside this one is we don't need it to see B of infinities. But later, it will go back again. But anyway, so we see small h is the element of hi. And we consider a shifted one. So bh of infinity is just shift b of infinity by h. So this has the following properties. For example, first of all, so the action bi tilde fi tilde is just commute with the summation by h. So it satisfies these conditions. So this means, so, just here b infinity. Sorry. B infinity. So we just shift BH infinity. So shift and the action is just compatible. Okay. So just shift action, and the action shift is just same. So basically, so B of infinity is connected, so BH of infinity also connected. Okay, and then so also the property is just always B of infinity, and BH of infinity is always it has intersections. And finally, so total union of these things just recover BA. So then by these things show that B and BI is just connected. Because, so, there are many BH, and all BH just has an intersection with B of infinity. So it means, so it can go back here, and then so it's go there. So it's connect. Every element just connected. Okay, so let's go to next subject, quiver-Hecke algebra. So to define the quiver-Hecke algebra, so we need many things, but so I omit many things, sorry. But anyway, so take index set, finite index set I. And the field K. And also we need some family of polynomials, two variable polynomials, Qij, Uv. It satisfies the following conditions, good conditions. So then, so we can define the quiver-Hecke algebras, or sometimes it is called KLR algebra. So, but today I only show here generators E nu. Nu is from here, and xk and tau I. Okay, so then they satisfy some relations. So, but I omit, sorry. And we consider the total summation is we denote by R here. So I haven't say beta. Beta is coming from here. Q plus. Q plus is the positive root semigroup. Okay. And the important feature of this algebra is it's graded algebra by defining grading like this. Okay, so this means modules we usually consider the graded modules. Categories just graded module categories. Okay. So the property of our modules. First of all, we define the Q shift factor. Q graded shift factor Q is just defined like it's a natural way. So it just shift 1 plus 1. And also sometimes, as I said, so graded modules has a grading. So morphism means just preserve the grading. It should be preserved. But sometimes we need to consider the different grading morphism. So in that case, we should just shift. And then so this has the same grading. So we can consider F is a homomorphism. Then so in such case, this shifted K is degree of F. And also we need conversion product. So we can consider the gmod category become monoidal categories. So M circle N is defined like such a induced up product. Okay, and then this means the head of conversion product. Head is just here, I explained here, the head is the modular quotient by its radical. And then circle. Circle is just the modules, the sum of all simple modules. So this is a circle. And also we say module, simple module M is real. What is real? If you consider M, circle M, it's still simple, so we call M is real. It's just a real number. And M is isomorphic to M star. M star is just dual, so it calls self-dual. Okay. And then categorizations. So we consider the two categories, R beta, gmod. It's a category of finite-dimensional graded R beta modules. And the beta G project is a category of finitely generated graded projective R beta modules. Then so we consider the functor EI, FI, just as defined like this. Okay, Li is one-dimensional simple R alpha I modules, one-dimensional. And then we consider the conversion product. This is the functor from here to here, and the EI is from here to here. Okay, then, so using this, so the Grothendieck ring gives the categorification of UQ minus G project, and the RG mode gives this AQN. Okay, and then categorization of UB of infinity by Lauda and Bajrani. So they defined like such data weight is just R of beta, beta. And epsilon I, phi I, tilde, it's defined by circle. And if I tilde, defined by head. Then, so we consider the family of self-dual simple modules in RG mode. Okay. Then these six tuple are, B, RG mode, tilde, this one, Fi tilde, this one, and weight, epsilon I, phi I holds the crystal structures, just I defined. And also, this crystal is isomorphic to B of infinity. Okay. Okay, now let us introduce the localizations. So to do it, we need, first of all, braiders. Take lambda is a Z lattice, and T is a lambda graded K-linear monoidal category. Okay, so this is the product. A graded braider is a triple C, RC, phi, where C is the object, and phi is a Z valued map on lambda. And the RC is a morphism like this. C circle X to some Q power X circle C. It's just C, X, X, just flip. So why we use R? Because it's almost R matrix on these modules, okay? And this, if they satisfy the following commutative diagram or plus some more conditions, but sorry, I omit. So we call this triple is graded braiders. But indeed, so today I omit, indeed this is a left graded braiders. It's C from left. But also we consider the right braiders. It's coming from C from right and then goes to left. But today we only need the left graded braiders, so I omit left here. But there are two left and right graded braiders exist. Okay, so next we consider some family of braiders, graded braiders, okay? Then we introduce some other Z lattice, sorry, I should say later, this lambda will become root lattice. So we apply these things to RG mode situation. So in this case, lambda become root lattice. And then gamma is a lattice which is goes to weight lattice. Anyway, so real commuting family of graded braiders is the following things. This family, Ci should be some object, and phi satisfies these conditions, and RCI satisfying these little complicated conditions, but important is RCIJ, CJ satisfy the Yang-Baksa equation on this triple product. Okay. Then so we can define some how to say something similar to the multiplicative set. So C alpha is from here, gamma plus. And then so this has such structure, so it's just saying that it has some kind of, up to Q power, it has multiplicative properties. Okay. Okay, then localization. So I omit many things, but anyway, so we defined some subset in gamma is D alpha beta. Alpha beta is from gamma. It's like this. Then so there exists some inductive system. It's inside here. Okay, so we define the localization of monoidal category T, denoted T tilde or like this. Here, object of T tilde is the product object T times gamma. It's like, you know, just to remember the localization of commutative ring. So you have ring R and also the multiplicative set S. And then we consider the pair S and R. It's just like this. So it become numerator and this become denominators. Then the homomorphism is given by the inductive limit of this one. Okay. Then finally we obtain the localization of this monoidal category. Okay. Then so we apply this to RG mode in our situation. Okay, to localize RG mode, we need real commuting family. So if you don't this one, so we cannot consider the localization. So we need how to obtain this one. First, we consider the Li to the n. It's just defined like this. Okay, so then so if I tilde n of m is defined like this, these formulas. Okay, so for dominant weight, lambda, and Weyl group M and W, Mk is defined by this formula. So we see somewhere this one, same thing. And then so the modules M, W, lambda, lambda is defined like this. Here, 1 is the unit object in category RG mode. Okay. Okay, so this definition doesn't depend on the choice of reduced expression, reduced word, okay? Here, if we take lambda is a dominant weight, lambda I is the ith dominant weight, Ci is also determinantial modules. Important feature is Ci affords an affinization. So I don't say anything about affinizations, but it's like affinizations of affine, quantum affine algebra's case. And then so if there exists affinizations, so naturally we have R matrix. RCI, Ci circle X to Q power X circle Ci. Okay. Then so we consider the localizations of RG mode. Okay. So consider this become the real commuting family. Then we consider the RG mode. RG mode, tilde RG mode. Okay. So I omit this part, so I don't have so much time. So anyway, so this gives the categorification of this category is so-called localized quantum coordinate algebras, coordinate rings. Okay, but sorry, I omit here. And then let's see the property of localizations. First of all, phi from here to localization is exact as a functor. And the ci tilde goes to invertible. Invertible means, so if you consider the product, so this gives the category equivalence. And the number 4 is important. For any simple object in this localized category, there exists before localized S, simple S, and weight lambda, and it's written in this form always. But this expression does not is not unique. You know, just a fraction number, 1 over 2 equals 2 over 4 equals 3 over 6. So fraction is usually no unique expression. So there exists, but this expression is not unique. Okay. But anyway, so important is there exist such expressions. Okay, so using this, so we consider the crystal structures on R tilde gmod. Okay, so we consider the self-dual simple object in this localized category. Okay, so one important feature is any simple object M, simple module M, so there is uniquely integer n. So q to the n, M is always self-dual. Okay, so this n is determined by M uniquely, so we denote its delta of M. Then the action of fi tilde on this product, this is a localized object, is naturally fi tilde acts on this one only. And ei tilde is a little different. If EIS is not 0, does not vanish, so we apply ei tilde on this part. But if EIS is 0, vanish, then so we just borrow some weight from here, lambda I star, and applying ei tilde on this side. It's just like, how to say, we consider a common divisor or something like that. Anyway, we defined such ei tilde, fi tilde, Kashiwara operators on this family of simple objects, self-dual simple objects. Then so other data is defined like this. Okay. Then finally we can show that this is become the crystal. And also we would like to know explicit structure of these crystals. So to next we should go here again, cellular crystal and HIs, just we defined. Okay, so we just recall that, so we are applying here, lambda is a dominant weight and mk is defined with this formula. Please remember where it is, where? Sorry, here. So here already we saw it here. Okay. Then using it, this gives us the h lambda. So indeed, so if we take lambda is a fundamental weight, this gives us the basis element hi. And then this formula has been seen already here. Sorry, where? So. No, where? Sorry, I forgot where it is. Here, sorry, here. This one. Okay, so this means hi corresponding to these modules, the dimension modules. Then so we see these modules and h lambda just correspond. So it means that this object in this family is corresponding to this one. h lambda plus phi h. Okay, so this gives us the isomorphism between this crystal and BI, cellular crystals. Okay, so I don't have so much time. So then next, that's the progress. So localized quantum unipotent category. Okay, so now we change the set to, we assume that, I assumed that G is simple, but now they are just symmetrizable Kac-Moody. Okay, so we consider the Y group element W. Then there exists so-called quantum unipotent coordinate category CW. So the definition is like this, but sorry, I omit. But important is if simple case, CW0 is just the whole RG mode. Okay, so this is subcategory of RG mode. Okay, so and unfortunately, this has the localization. So we can consider the CW tilde. Okay, and then so localization factor QW from RG mode to RGW CW tilde. Important is if we restrict this one to CW, so it is fully faithful. And the interesting feature is this is very big compared with CW. But if we consider the localization both, this localized category and CW tilde are category equivalent. So it means so by localization factor, many objects goes to 0. Then so that kernel is described explicitly like this. Indeed, so what is BW? BW is defined by using the module crystal. But sorry, today I omit the definition of the module crystals, but that one is described very explicitly like this. Okay, the problem. So this localized category has crystal structures, yes or no? And if yes, it is isomorphic to these cellular crystals or not? The answer is yes. Okay, this is a progress. To solve these problems, we need 3 ingredients: rigidity, and affinization, and R matrix. Okay, so these 2 terms already appeared, but the rigidity not yet appeared, so I don't have so much time. So rigidity is maybe, so it's very famous, so people here are maybe familiar. So, but anyway, so this is T is a monoidal category, X, Y is objects, and epsilon and eta is a such morphism. Then so pair X, Y is called dual pair, or X is left dual to Y, or Y is a right dual to X. If they satisfy the following, these 2 compositions are just identities. So in that case, we say X, Y are dual pair. And the definition, so left rigid, category T is left rigid if any object has left dual. And right rigid means any object has a right dual. And both, we call this category is rigid. So it means any object has left dual and right dual.
They do not coincide.
Pardon?
Left dual and right dual are different objects.
Different, yeah. Not same. Then so quiver Hecke algebra R, so they show that CW tilde is rigid. Okay, so this is very important property. Okay, and then so now we go enter the our situation. So take C is a monoidal category, so general monoidal category, but it has some good conditions. But I omit. Then so we extend this one to pro C. Pro C is just we add some projective limit to C, and then we just extend C. And then so inside here, so we consider the Z KZ module things here. And then so we add some conditions, and then we'll have a plural coherent category. And then finally, we have FZC. Okay, so this is our target. So object MZ in this category is called a fine object. This quotient is a object in C. And a fine object MZ with rational center. Rational center is just kind of R matrix. It's called affinization of M. Okay. So important feature, you know, C is rigid. FZC is also rigid. So because before this one, so we consider the R matrix or affinizations. It's just before localizations. After localizations, we don't know there exist affinizations or there exist R matrices, so we don't know. So we need some general theory should be here, so we need it. Anyway, so I don't have so much. And so affinization, so affilial is a real and it admits affinization. We call this is affilial. Affilial M and simple N. The conversion product have simple heads and simple circles. However, this morphism just one-dimensional, and then its generator is R matrix. Okay, so from here to here, just only one, up to scalar, one element is just R matrix. How to obtain it? We need to renormalize R matrix, because so naturally, so there exists a universal R matrix like quantum algebras. But if we are applying it universal R matrix on this product, so some of them become just vanish, goes to zero, naively. So we don't want to do that. So first we consider the renormalized R matrix. It's defined on affinizations. So affinization is like, you know, here's modules. But affinization is like this. And so naively, so it goes to zero, but some part non-zero. Then so we take here, and then so we just adjust the z power. Then Z goes to zero. Z goes to zero, so we have R matrix, non-trivial R matrix. Okay. Then using it, we have how to say, some good tools to solve the problem. Okay, so we need it. I don't have so much time. Anyway, these values is defined by R matrix, R tilde. These are some kind of invariants on these modules. Okay, so maybe we don't name them. Anyway, lambda, tilde, or something like that. Then, using the rigidity and R matrix on CW tilde, we can define the crystal structure on these self-dual simple objects. Okay. By, for example, EI tilde on X is from here, is defined like this. Here, phi I, x, I, sorry, I don't give the definitions, but anyway, it's some integer. And then this is head, it means, and D is the light dual of this localized objects, QW, Li. Okay, so this is the definition of EI tilde. Or also we can define FI tilde star, EI tilde stars. Okay, and then they give us the crystal structures on this family. And finally, we can show there exists isomorphism between here to here. Okay. And then as a corollary, so we can show that this crystal is also connected, as we stated. Okay, so, okay. Thank you.
A few minutes for questions.
I have a very simple question. At the beginning, you mentioned a crystal graph.
Yeah.
Can you come back to that definition? Is it looking like the same as a Cayley graph when you have, for instance, a group where you take this element of the group as being the nodes and linking two nodes, if there is an element linking that element to the other one, you put there an arrow, and the arrow is, of course, the element that maps one object to another. Is it like this?
Sorry, I'm not sure the can graph. Yeah, so sorry, so I'm not sure, yeah. Okay.
We have time to another question.
It's not with our speaker.
Thank you.